Hey, the topic of this video is skydiving and how that relates to terminal velocity, if you've ever heard that term before. Well, let's imagine for a moment that you are in a hot air balloon way up high in the air and you jump out. We'll assume you have a parachute, but you haven't opened it yet. So you jump out. What happens to you? Well, here you are, and that red arrow is describing the force of gravity pulling down on you. In other words, your weight. And since that first instant you let go of the basket of the balloon, that's the only force acting on you, and therefore that is the net force. And you're going to accelerate downwards at a rate of 9.8 meters per second. But as you gain speed, there's another force that appears, namely drag. And drag is a force, unlike regular friction, solid surface against solid surface. Drag depends on how fast you're going. The faster you're going, the more drag there is. So as you speed up, as you go faster in the downward direction, drag is going to be increasing and pointing up opposite your motion. So when you're still not going very fast, it'll be up, but not enough to equal your weight. But there is an upward force. And I hope you can see then from this that you've got a downward force equal to your weight. That's not changing. The upward force, that's the drag, there's still going to be a net force downwards. But that net force is going to be less than your weight, and your acceleration is going to be less than 9.8 meters per second. And but as you continue to speed up, eventually you reach a point where you're going so fast that your drag actually equals your weight. And in that case, your net force is zero. Now, that doesn't mean you stop. You don't stop in midair. It means you stop accelerating. And so we call that terminal velocity. We call that terminal velocity for a typical human being in the Earth's atmosphere in that kind of splayed out skydiving position. That's about 120 miles per hour is the terminal velocity. And it's also terminal velocity because that's the speed with which you're going to hit the ground if you don't open your parachute. So you really want to have a parachute if you jump out of a balloon or airplane. So what do you do when you open a parachute? You're moving very fast, maybe 120 miles per hour, and all of a sudden this big sheet of fabric appears above you, attached to you with ropes. And so there's going to be a huge amount of upwards drag. And that force means that there's going to be a net force upwards. You've got this huge upward force. Still your weight is pulling down, but in comparison to that drag, in that instant, the net force is upwards. And since you are moving downwards, but there's a net upwards force, that's going to slow you down. And as you slow down, the drag decreases. And you will slow down until the drag equals your weight again. And you're once again falling at terminal velocity. But now with the parachute out, your terminal velocity is about 20 miles per hour instead of 120 miles per hour. So that is the process of skydiving. You reach terminal velocity twice, once without the parachute open and once with the parachute open. It's just that at 20 miles per hour when you land, you don't die. You don't die, and you can break an ankle or something if you land wrong. You do have to be careful, but that's the speed that you're going to land with. Now, if we were to graph the speed as a function of time for a skydiver, then you gain speed. Initially, you gain speed at a rate or a slope on a velocity graph of 9.8 meters per second. But as the drag increases, you level off at some constant speed, about 40 meters per second. Again, that's about 120 miles per hour. But then you open their parachute, and then your speed rapidly decreases. And I've been skydiving, by the way, and the first time I did it, I had pulled muscles. My shoulder and muscles there and in the upper back were really sore for several days afterwards. So it's a jarring, jerk upwards when that parachute opens, but then your speed drops to a much slower speed. So a couple questions then. What would be different if instead of a person falling, if it were a leaf? And here are your choices. I'm going to ask you a series of questions. So pause after each one and think about what it would be. So if it's a leaf, have you ever seen a leaf falling from a tree? It kind of flutters down rather slowly. So the terminal speed is slower for a leaf. What if it was a bowling ball instead of a person? Bowling ball's heavy, it's compact. It's going to have to go really, really fast in order for the air resistance to equal its weight. So it will reach a terminal velocity or terminal speed, but it's going to be faster. What if you were skydiving on a planet with no atmosphere? So you go to the moon or Mercury, for instance, that don't have atmospheres. What would be different? Well, there would be no terminal speed. You would be accelerating, gaining speed constantly until you hit the ground, in which case you would lose a lot of speed very rapidly. And so this experience of skydiving without reaching a terminal velocity can be simulated on the Earth by doing it inside an airplane. So I mentioned I've been skydiving, actually jumping out of an airplane in the atmosphere. But I also, some years ago, had the opportunity to fly on an aircraft contracted by NASA. They call it the Weightless Wonder. It's informally known as the Vomit Comet, but NASA really does not like that name. But it's actually the name most people know the airplane by. If you've heard of it, you may have heard of that name. And so what this is an airplane that does a trajectory where it follows parabolas. And so it will arc up and then follow a parabola, and it actually follows the parabola that you would follow if there were no air resistance. And so the airplane stays around you and protects you from drag. It protects you, it shields you from the air resistance. And so at the top of each one of these arcs, you get about 20-25 seconds of free fall with no air resistance, no drag. And therefore it's often called weightlessness. And because you're floating inside the airplane, you're floating around as if gravity were turned off. But of course you are accelerating towards the ground. And so there's a limited amount of time that the airplane can do that before it's going so fast that the wings are going to rip off. And so about 20-25 seconds, and then the airplane has to come out of the dive, and doing that pull up, everyone inside is kind of plastered to the floor with about 1.8 or 2 Gs. And so I had this opportunity as part of a team that I put together for designing an experiment, and this was an opportunity to fly science experiments on this airplane. But what I'd like to do is to show you a little bit of video, what it's like inside this airplane during one of these flights. This was a video taken during my experience. And so this is the airplane. NASA used to have its own airplane for doing this, but recent years they've been contracting it out to an outside company. So you can actually pay this company a few $1,000s and go on one of these flights just for fun. And I think they fly out of Las Vegas. Let me skip ahead. You don't have to see the whole thing. Here we are loading into the aircraft. I'm going to skip ahead. There I am. And this is during the flight. This big box here actually contains our experiment. And I'm down here. Here are my team members. So this is Jason. He is manning this camera here that's looking at our experiment. But you can see the effect of weightlessness, quote unquote weightlessness. I'm working the experiment through these holes in the side. And the nickname of Vomit Comet is apt because you're going from 0G to 2G and 0G to 2G repeatedly. And in our case, I think we did 20 to 25 of those cycles. And a good fraction of the people actually got sick, hence the name Vomit Comet. That is typical on these flights. And I came this close. I was able to not get sick and stay on my experiment, but I was not feeling well for much of it. Whereas other folks on the flight just they're doing somersaults and floating through the air and just having a delightful time. And so anyway, that's an example of free fall with no air resistance. And so I just wanted to share that. But during that experience, what I felt is butterflies. When like if you're ever in a roller coaster that goes over the top of the hill, or in a car going too fast, cresting a hill, you feel a little bit of butterflies. Your stomach drops out. Well, that you get that feeling. It's like, oh, the floor is doing something it shouldn't be. It's running away from me. And so it's very intense butterflies is the feeling. And then when the airplane pulls out of the dive, you feel very, very heavy, and you're plastered against the floor. The feeling during skydiving when you jump out of the airplane into the atmosphere is very different. You get those butterflies for the first second or two, but as you gain speed, as the air resistance increases on you, and you get more to this situation here, your stomach, your innards feel perfectly normal. And yes, it's very windy because you're moving through the air at 120 miles per hour, but you don't feel funny in your gut. And so the feeling of 0G in the Vomit Comet Weightless Wonder is very different from the feeling you have when you're skydiving and you're at terminal velocity.